This video is on the Doppler effect. Question 1. Define the Doppler effect. The Doppler effect is the change in observed frequency from the change in relative motion between an emitter, source, and an observer. When describing the Doppler effect, do not mention wavelength, only mention frequency. Question 2. Draw a wavefront diagram for a moving source and stationary observer in front of the source and behind the source. So the two observers who are recording the frequency and wavelength are not moving, they're stationary, they're in front of this moving source and behind this moving source. You could see the wavefronts next to observer 1, they're increasing their wavelength. Therefore, they're decreasing their frequency because V equals lambda F. So V is a constant. Lambda gets longer, F gets shorter. Remember, wavefronts are distance between crusts. Look at observer 2. The wavefronts are getting closer to each other. So the wavefronts, which are the distance between crusts, show that the wavelength is decreasing and frequency is increasing because V equals lambda F. V is a constant. Question 3. A car travels to the right with a constant speed and emits a constant sound with a constant frequency. The car moves away from observer 1 and towards observer 2. So observer 1 will detect a longer wavelength and a decrease in frequency as compared to the source. Observer 2 will detect a shorter wavelength and an increase in frequency as compared to the source. The speed of sound measured by observer 1 will be equal to the speed of sound measured by observer 2, since the sound wave travels in the same medium. Question 4. Draw a wavefront diagram for a stationary source and moving observer in front of the source and behind the source. So now the car is not moving and someone is running with a constant speed towards the source. That's what the wavefront diagram looks like. It looks like perfect circles. And observer 1 on the left and observer 2 on the right detect the same frequency and wavelength. The speed is constant. Question 5. Describe the equation delta F over F equals delta lambda over lambda is about V over C and define each variable. So we can use the above mentioned equation if we have objects traveling much slower than the speed of light. We can use this equation when emitting a microwave at a plane. Some of the microwave bounces back and the speed of the plane can be determined. In this case, the right hand side should be 2V over C. So use this equation for electromagnetic waves here. So V is the speed of source or observer, C is the speed of light, F is the emitted frequency, delta F is a change in observed frequency. Lambda is the emitted wavelength, and delta lambda is a change in observed wavelength. Question 6. Describe the term redshift. If light moves away from an observer, then the wavelength of that observed light will increase. We call this redshift. If you look at an emission spectrum, then the lines are shifted towards the red side. Recall Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet, and indigo violet means purple. And recall that red light has a longer wavelength and lower frequency than blue light. Question 7. Describe the term blue shift. If light moves towards an observer, then the wavelength of that observed light will decrease. We call this blue shift. Okay. So if you look at an emission spectrum, then the lines are shifted towards the blue side. Question 8. Describe the term expanding universe. Astronomers observe stars undergoing a redshift. The stars are moving away from the Earth, so they believe that the universe is expanding. Question 9. A train approaches and then passes a train station with a constant speed. During the whole time the train is emitting a sound. Draw a frequency versus time graph of the observed frequency measured by the observer at the train station. So the frequency is a constant when the train has not approached the train station. Once it approaches a train station, it goes vertically down, and then it continues to emit a constant frequency. You see, frequency is constant before and after the train station. Question 10. A train approaches and then passes a train station with a constant speed. During the whole time the train is emitting a sound. An observer is outside of the train station as seen in the image below. Draw a frequency versus time graph of the observed frequency measured by the observer outside of the train station. So here you could see the observer is outside of the train station. You could see the slope is much less in magnitude than in question 9. In question 9, the observer is at the train station. In question 10, the observer is outside of the train station. The curve is more horizontal or less steep. Question 11. An accelerating train approaches and then passes a train station. During the whole time the train is emitting a sound. Draw a frequency versus time graph of the observed frequency measured by an observer at the train station. If it's accelerating towards the train station, it's going to look something like this. Question 10. A decelerating train approaches and then passes a train station. During the whole time the train is emitting a sound. Draw a frequency versus time graph of the observed frequency measured by an observer at the train station. Because it's slowing down, the observer is going to detect a decrease in frequency. When the train passes the observer, it's slowing down, so you could say it's being pushed to the left towards the observer. That's why the observer is going to detect an increase in frequency. Question 13. List some practical uses for the Doppler effect. Detecting the speed of an automobile, monitoring aircraft and boat movements, tracking movements of storms, measuring blood flow, calculating speeds of stars and galaxies. Question 14. An element on Earth emits a spectral line which has a wavelength of 600 nanometers as measured by an Earth observer. Calculate the wavelength of the same spectral line if it is observed from a galaxy moving away from the Earth with a speed of 0.2 c. So that's what we do. We're going to use this equation. This solution makes sense because the wavelength has increased because it's moving away from us. Question 15. An element on Earth emits a spectral line which has a wavelength of 600 nanometers as measured by an Earth observer. Calculate the wavelength of the same spectral line if it is observed from a galaxy moving towards the Earth with a speed of 0.2 c. So you see in question 14 it's lambda minus 600. 15, it's 600 minus lambda. So that was switched. Now if we're moving towards the Earth, we should have a decrease in wavelength. And that's what we got. The solution makes sense because the wavelength has decreased. While in 14, the solution makes sense because the wavelength has increased, because we're moving away from the Earth. Question 16. An element on Earth has one emission wavelength of 8.67 times 10 to the minus 7 meters. The same element, when detected from a moving distant galaxy, has the same emission wavelength of 3.09 times 10 to the minus 7 meters. Is a galaxy moving towards away from Earth? Well, we could see that the wavelength has decreased, so the frequency has increased. An increase in frequency means that the object is moving towards the Earth. So this is an example of a blue shift. Part B, what is the speed of this moving galaxy? So we're going to use this equation. And we know delta lambda because they gave us both lambdas. And we just solved for v. This is quite fast. Question 17. A stationary police car emits a microwave with a frequency of 3 times 10 to the 10 hertz to an approaching car. The microwave is reflected off the moving car and is received by the stationary police car. The police car detects that the frequency is altered by 6 times 10 to the 3 hertz. Part A, what is the wavelength of the microwave being emitted by the police car? So just use V equals lambda f. We know this is the speed of light. Solve for lambda. Part B, what is the speed of the approaching car? So we're going to use this equation. And remember, this V becomes 2V because of the frequency shift. It bounces back. So we're going to solve for V. You get 30 meters per second about. How much has the wavelength altered? So delta lambda is lambda V over C. Question 18, describe the equations for the Doppler effect. So if you have a moving source and stationary observer, we have this equation here. If we have a moving observer and stationary source, we have this equation here. So f prime is not the derivative of f. Okay. F prime is the measured frequency, observed frequency. Okay. So there are 4 cases which are used for sound. A source moves towards a stationary observer. Here the denominator has a minus sign, so f prime gets bigger. Case 2, a source moves away from a stationary observer. Here there's a plus sign in the denominator, so f prime becomes smaller. Case 3, an observer moves towards a stationary source. Here there's a plus sign in the numerator to make f prime larger. Finally, an observer moves away from a stationary source. You can see the numerator has a negative sign to make f prime smaller. So remember, frequency is related to pitch. When you see the word pitch, know that it's frequency. Both amplitude and intensity are related to loudness. When you see the word loudness, think of amplitude and intensity. Question 19. Usain Bolt runs towards his physics class with a constant speed of 10.44 meters per second while blasting music from his boombox, which emits a frequency of 440 hertz. What is the observed frequency and wavelength detected by the students in his physics classroom? Okay, so we use an equation where we have a moving observer and where we have a moving source and stationary observer. Usain Bolt is the moving source, and the students in the classroom are the stationary observers. So we use this equation to get an answer. Question 20. Usain Bolt runs away from his physics class towards the cafeteria with a constant speed of 10.44 meters per second while blasting music from his boombox, which emits a frequency of 440 hertz. What is the observed frequency and wavelength detected by the students in his physics classroom? So you can see in question 19, students observe a wavelength of 0.75 meters. When he runs away, it's 0.797 meters. The wavelength has increased. And you can see the frequency has decreased. It's 427 for this one because he's moving away. It's 454 for this problem because he's moving towards the detector. Question 21. Usain Bolt runs towards his physics class with a constant speed of 10.44 meters per second. He can hear his physics teacher lecturing with a frequency of 440 hertz. What is the observed frequency and wavelength detected by Usain Bolt as he runs towards his physics class? The speed of sound in air at sea level is approximately 340.29 meters per second. So now Usain Bolt is the observer and the source is stationary. Question 22. Usain Bolt runs away from his physics class to the cafeteria with a constant speed of 10.44 meters per second. He can hear his teacher continue to lecture with frequency of 440 hertz. What is the observed frequency and wavelength detected by Usain Bolt as he is running towards the cafeteria? So, in this case, Usain Bolt is running away from the stationary source. Question 23. An emitter at rest emits a sound wave of frequency 3 times 10 to the 4th hertz towards the car. The wave is reflected back to the emitter. So it bounces back. The emitter now becomes a receiver. The receiver receives a sound wave with a frequency of 2.9 times 10 to the 4th hertz. And the speed of sound is 3.3 times 10 to the 2nd meters per second. Determine the speed of the car. Okay. So let's understand what's going on. Maybe drawing a picture is best. The receiving frequency is lower than the emitting frequency, so the car is moving away from the emitter. Okay. The car acts as an observer. Okay. Meaning first the car gets the wave, then it's going to emit the wave. So it's the moving observer. Let's determine the frequency the moving car receives. And now the car is acting as an emitter. So now it's a moving source. And determine the frequency the emitter or receiver receives. It's a lot of algebra. You have a minus u on this side, and we have a positive u on this side. Question 24. An emitter at rest emits a sound wave of frequency 3 times 10 to the 4th hertz towards a car. The wave is reflected back to the emitter. The emitter now becomes the receiver. The receiver receives a sound wave at the frequency of 3.1 times 10 to the 4th hertz. Determine the speed of the car. So the receiving frequency is higher than the emitting frequency, so the car is moving towards the emitter. So step 2, the car acts as an observer. So we're going to use this equation. Step 3, we're going to determine the frequency the moving car receives. That's this. Step 3, the car now acts as an emitter. So we get this. So we get this mu sub 0 and mu sub s. Set them equal to each other. Now it's just algebra to solve for u.